Yes, Kevo. Hi. Welcome. Can we check in? Because we have the cut tomorrow. We need to take limited time. If it goes too far, it could be 1 hour. But I want to take less than an hour for us to discuss the essays. Kevo, welcome. So we are having the BMLS regular. Yeah, Nadja. Just tell them to log in very fast so that you don't waste time, The cut is tomorrow morning, so I don't want us to get exhausted. I just explain what we need to write, where, for the essays. Welcome. I'm going to start after 3 minutes. Today I'm not even giving 5. Agnes, yeah, welcome. Yeah, just tell them to log in, please. Maybe there are some people who do not want to come on board, so we can just proceed 3 minutes after. I just explain much on number 12 and the essay parts, and then we'll be done so that we can go to sleep, and then tomorrow you wake up when you're fresh. Class reps, the class rep for BMLS, who has been doing a good job by reminding me, because yesterday I forgot. I have a lot I can forget, so I told her to let me know. And he did a good work by informing me in the morning. Yeah, Cornelius, yes, welcome. Oh, Nadja, are you the class rep who we kept on communicating with? Thank you so much. Thank you so much for sacrificing for the whole group and for always updating me. So we are going to start. I have to start because I don't want to waste time. That's why I always like having the revision days before the cut so that the students can revise and they have time. Thank you so much. Alex is there. Alex is for the other class. Welcome. Let them log in, but then I'm proceeding with question number 12. Whatever is there on the board should not confuse you. I had the other students of mine. This is genetics, so don't worry about whatever is on the board. We are going to proceed. Question number 12. And in question number 12, there is a question there on fatty acids. We are not going to set that in cut 1 because we haven't covered it. So I'm just going to tackle the ones which we have covered in class. Huh? So for question number 12, I said in reference to structures, distinguish the following: beta L mannose, beta L galactose. I mentioned that when I talk about beta and alpha, you have to draw your monosaccharide in cyclic form. But if it is without beta or alpha, draw the linear form. So you talk about the D and L. That one you have to draw in linear form. But immediately I add the word alpha or beta before the structure you have to draw, then it has to be a cyclic. So the next thing which you have to look at is if it's mannose, it is going to form a 6-membered ring, It is an aldose. An aldohexose. So we are talking about mannose, but then in this case, we are talking about beta. The carbon atom number 1, if it is above, the OH above, that is beta. You've already placed it nicely. Carbon atom number 6 will sit here. Carbon atom number 5, already there is a hemiacetal formed here. So we are going to work on carbon atom number 2, number 3, and number 4. So we see the position of the OHs in this cyclic form. So I'm talking about L-mannose. If you look at the D-mannose, at carbon atom number 2 and number 3, It is always to the left. So whatever is to the left will go inside, but whatever is to the right will go outside. So we are talking about L-mannose, L-mannose, L. If you know the linear form, the cyclic form will be very easy. Look at that. We are talking about beta. Look at the carbon atom number 1, the OH is above. Already it's forming a pyranose, 6-membered ring. At carbon atom number 6, where CH2OH is up there. And now, since it is L-mannose, you know, for D-mannose, at carbon atom number 2 and number 3, they are always, the OH is to the left. So whatever is to the left is always inside the ring. But now, it has to come to the right because it is L-mannose. That is how you draw L-mannose. It means for beta L-galactose, beta L-galactose, I'm going to use the same structure which is on the board because it's still beta. The OH is above there. But now, if you talk about L-galactose, beta L-galactose, it means at carbon atom number 4, at carbon atom number 4, at number 2, it will be inside. That is beta L-galactose. You know, it will be saved. These ones will be saved, so you'll know. When you follow my live videos, you'll be able to know that what Madame drew first was beta L-mannose. This one is beta L-galactose. The position of the OH at carbon atom number 3 and number 4 is to the right. So it will come outside the ring. So we've drawn beta L-mannose, beta L-galactose. Remember, if you talk about beta, the OH above at carbon atom number 1. If you talk about alpha, the OH below at carbon atom number 1. But now, mannose and galactose are going to form the pyranose, the 6-membered ring. So if we know how to draw the linear form, already at carbon atom number 5, the hemiacetal forms the OH there and the carbon atom number 1. Carbon atom number 6 sits up there. Carbon atom number 1 determines alpha or beta. So you play around with carbon atom number 2 to number 4. That's how simple it is. Then I tell you, skip Roman 2, which talks about the fatty acids. I'll ask in cut 2. Go to Roman 3. I'm saying you draw alpha D glucosamine. Alpha D glucosamine. I told you these are the amines of the sugar amines. So if you look at glucose, 3, 4, 5, 6. We are talking about D glucosamine. I told you at carbon atom number 2 to your right. That is how glucosamine will look like. That is glucosamine. But now I've said draw the alpha. Draw the alpha D-glucosamine. So the 6-membered ring is there. Alpha, OH below. At carbon atom number 2, the NH will stand here. Down, it's outside. At carbon atom number 3, carbon atom number 4, number 5, then number 6. Let me put the OH well so that you don't say, Madam, you are the one who drew it like that. Simple as that. Don't cram. Master how the structure comes about. It has to form a 6-membered ring. The first point. Because we are talking about beta and alpha. But now, if you start with a linear form, drawing the cyclic form is very easy. So just twist it in clockwise direction. Look at the OH down there at carbon atom number 1. It tells about the alpha. Look at the amine group. it was to the right. So it will come outside the ring. The way we draw normally the glucose, the D-glucose, the OH is to the left. It is go inside at carbon atom number 3. Number 4, the same position where it is for the amine group. Number 5 already formed the hemiacetal. The 6th one sits up there. Then, yes, people are still coming. Hi, everyone. Ochieng, Vivian. Hi. We are proceeding. Oh, there is even somebody called Kasongo one term. Okay. We won't enter into politics, but we are saying hi back. Huh? We also have Hassan. Hi. Sauda. Hi. I wanted us to work within 1 hour so that students can go and relax, because tomorrow's a cut. You don't need to work until late. So that's how we can draw the alpha D-glucosamine. Let us do beta D-galactosamine. So I start with the galactosamine first. I'll start with the galactosamine. What happens? Galactosamine is simple. Just add OH here. You see? The same structure for glucose. We're just going to change things which are simple. This is galactosamine already on the board, which I've drawn. So it means put OH here for galactosamine. But now it is alpha or beta. Let me see. Beta. OH above. Simple as that. Don't cram, master. No, I'm sorry, Hassan. You didn't remind me, so I forgot. By the time class reps were consulting me, I'm so sorry. I couldn't remember. So that's why I told the class rep BMLS, kindly just remind me today morning so that I can put it on my diary. I already forgot. If you don't remind me, I can't remember. I'm sorry about that, but let's tugange ajayo. So look at the structure on the board. To your left is D-galactosamine. The amine group is still replaced by the OH at carbon atom number 2. So the amine group in glucosamine is the same as the amine group. The position is the same as the one in galactosamine. But now you are drawing the cyclic form and you are talking about a beta D-galactosamine. That's how simple it is. And then I talk about D-manosamine. I'll draw D-manosamine before I can draw the N-acetyl glucosamine. So we are still using the same structure, but then while you'll be seeing the video, the live video, the recordings, you'll be able to see the difference because it will be able to show. It won't show the same one. So we are talking about manosamine. You know, manosamine, we talked about it looking like this. Oh no. So this H should not be there. OH should not be there. So it should be, that is galactosamine. Sorry. The OH I didn't rub this side. So that is galactosamine. If you want manosamine, now the NH2 come this side. Here we have H. The OH at carbon atom number 4 will come this side. That is D-manosamine. This is D-manosamine. D-manosamine. At carbon atom number 2, where mannose is an epimer of glucose, that is where that OH you substitute with amine. And then the other ones are the structures of mannose. So that's how simple it is. D-manosamine. So it has to be a linear form. And then we talk about N-acetyl glucosamine. N-acetyl glucosamine. Glucosamine was like this. So N-acetyl glucosamine. You can do this. CH3. Let me rub this one so that it doesn't bring confusion. You see, you balance the bonds, meaning in long form, it is something like this. And then the hydrogen surrounding the carbon. So you have N-acetyl glucosamine. So you can be asked to draw any of those amino sugars, and we should be able to draw them. If you look at glucose, just draw glucose very well the way you can draw D-glucose, but then putting the amine group, it is at carbon atom number 2, where the OH is to the right. The same with galactosamine, the way galactose, D-galactose looks like. Leave the amine group at carbon atom number 2. But then for monosamine, then it means where it is an epimer, that carbon atom number 2, where it is epimeric to glucose, put the amine group. And then for the N-acetylglucosamine, that's how simple it is. So if you have to understand well on the linear form, drawing a cyclic form is very easy, my dear. We are straight to essays. I said I don't want to take much time because I don't want students to get tired until tomorrow morning. They won't be able to remember much of the things. But then I said the cut is going to start at 10:30. So we should be there all at 10:30. But let us look at the essay. I'm trying to scroll down my questions. I think it was criteria for naming of monosaccharides. And you know, I have to set, it can be water or it can be buffers. I'm going to set any of them. But please don't write Mwakenya. Don't write. Just try to understand whatever we are revising here. I don't know why it is taking much time to show from my laptop. Just a minute. Yeah. So it says, using 4 structural examples in each case. 4 structural examples in each case. Discuss the 2 criteria which naming of monosaccharides is based on. And it's a total of 20 marks. You can see 4 structural examples. This one, even by not drawing the structures, because we've now seen how to draw the D-glucose, how to draw on that Saturday, sorry, we drew the dihydroxyacetone, we drew glyceraldehyde, we drew the glucose, the mannose, we have even drawn them today. So in this case, first you talk about naming of monosaccharide is based on the functional group. Under functional group, I need 4 structures, meaning 2 ketoses, 2 what? Aldoses. So if I talk about 2 ketoses, you can draw a ketotriose, a ketoexose. So the ketotriose I'm talking about is dihydroxyacetone. I could remember in class where we had the table, the number of carbon atoms, the functional group. So I said using 4 structural examples in each case. So you have to talk about the functional group. That one will give you a mark. Under functional group, you'll talk about the aldoses. And then you explain aldoses, they have an aldehyde group at carbon atom number 1. And then you will give examples, meaning the names of the structures you are drawing. If it is dihydroxyacetone, if it is glyceraldehyde, if it is D-glucose, if it is D-fructose, give the names. It's going to give you marks. Then huge marks will go for the correct structure. Now you know how to draw the monosaccharides. So the functional group will be captured there. And then you have to circle. If, for example, whatever we see here, for example, will be an aldohexose. You will circle and say aldehyde group. After explaining that the aldoses, they have the aldehyde group at carbon atom number 1, you draw the structure and then just circle where the functional group is, and then point and say aldehyde group. Same, whatever we drew last time, I told you the last one has to be CH2OH. That is glyceraldehyde. If you look at your notes, just circle the last bit and you'll be able to talk much about an aldotriose. Then go to the the ketosis, you will have a ketotriose, which is known as dihydrogenone. Just circle here and tell me a keto group. So you talk about the ketosis. At the second carbon atom, you have the keto group, the examples dihydroxyacetone and fructose. That one already meets the 4. I need 4 structures, meaning 2 for aldoses, 2 for ketosis. Then go to based on the number of carbon atoms in the main skeleton, because it's 20 marks. In number of carbon atoms, based on the number of carbon atoms in the main skeleton, start by mentioning 3 carbon atoms, say triosis, 4 carbon atoms, tetrosis, 5 carbon atoms, pentosis, 6 carbon atoms, hexosis. Then draw the structures of those triosis, pentosis, hexosis, and mention their names. You will get the marks. I will not deny you any mark. So the structures will go with many marks. That is well understood. If you have any concern, kindly you can just write for me there in the chat. I'll be able to explain. Discuss any 2 homopolysaccharides. The homopolysaccharide, we only discuss the homopolysaccharide. For the heteropolysaccharides, that is what I gave as the assignment. And you'll see the components of the amines of those sugars. On ketosis, are we drawing all of them? No. I said, Faith, I've said, the instruction, based on the instruction says, using 4 structural examples. 4 structural examples. 4 structural examples. It means, based on functional group, give me 2 of the ketosis. Give me 2 of aldoses. Based on the number of carbon atoms, draw all the 4, because in class we did triosis, we did tetrosis, we did pentosis, we did hexosis. So whatever we did not draw at the pentoses. And the pentoses, the tetroses are very simple. I'm going to answer all those questions I'm seeing. If you have to know how to draw these structures, even before you even consult anyone, the last carbon will be CH2OH. You get? So you have to go to that. That's why I told you have to go and read and see the name of that one, whether it is the one which is known as erythrulose or erythrose. But drawing will be the same pattern. The last one, if it's a tetrose, the 4th one will be CH2OH. It means for the ketosis, ketotetrose. That's how simple it is. I'm answering the question for ketose. I withdraw. No, I'm answering the question for Nasra. Nasra, I'm answering your question. The functional group shows there. Tetrosis, there's 3 carbon atoms. The last carbon will be CH2OH. In between here, put the OH to the right, left, H to the left. Are you supposed to draw both linear and cyclic structures? No. I'm drawing because I'm trying to make it easier for you how we are twisting in clockwise direction. If you are asked a beta D-glucose, go straight and draw for me the cyclic form. You have your rough work part. Do rough work, draw linear, and then give me the final answer. Because if you give me those 2, I'm going to give you a very big wrong, because you're already confused. You have to tell me which one is the answer. Or just by mentioning that this is the beta, as much as I'm talking about D-glucose, but then at this end, you asked me about alpha D-glucose. So even if you name it, if you have both linear and cyclic, but you name You write up there, beta D, I'll give you a mark for that, whatever which you've written. But if you don't write anything, but you give me those two structures, I will not give you a mark because you are waiting for me to decide for you which one is correct. Charles, that is how it is. So if you give me the two, maybe you are using the linear one to understand how to draw the cyclic one, and I specifically ask for the cyclic one, kindly write it up there. Now, this is beta D, this is alpha L, you get? I'll give you a mark. But if you don't write anything up there and you have the two structures, then we will not be moving in the same direction. Falling scap will be provided. What type of question is that? Don't joke. We are here to serious things. Thank you. We are here for serious things. Wait for things to happen tomorrow. It is my headache whether the full scap will be there or it will be printed. Our work is to get what we need to write. I think I try to answer the ones which I've seen. Keep on chatting. If it concerns whatever we are doing now, it's okay. Please don't distract, because some students are trying to understand how they can do the cuts tomorrow, what they need to answer. We are talking about any two homopolysaccharides. You could remember on hydrolysis, they give one kind of monosaccharide. So we had the cellulose, we had the glycogen, we had the starch. And the reason why I have put 10, starch will take much of the marks. If you discuss starch, you are going to discuss about amylopectin, you are going to discuss about amylose, and then you have to talk about it is the plant, the type of carbohydrate found in plants. And then you have to talk about the amylopectin being branched. It has both the alpha 1,4 and 1,6. But then you also have to talk about the component being the alpha D glucose, because in cellulose, you saw that it was a beta D glucose. And then in amylose, we find that it is linear. It has only alpha 1,4. But also to mention, if you talk about amylopectin, which falls under starch, it being less branched than glycogen. And then you can also discuss about glycogen, still the alpha D glucose, still branched as amylopectin. So this one is a direct one. This one, no structures. But you have to describe, that is what I want you to describe. The components, the type of glycosidic bond. It is found in plants or animals. That is how important it is. So you can discuss any. You can have cellulose and glycogen. You can have glycogen and starch, whichever. But I'll be giving half. But most marks will go for starch because it's a bit, it has a lot of information. I said that is 10 marks. And then the Roman 2 of that question now talks about specifically classification of monosaccharides, or naming of monosaccharides, not classification. It is naming of monosaccharides based on the functional group. So you could see the other one was combining functional group and the number of carbon atoms. So here I said, using structures, discuss monosaccharide classification. It's even open, but then it should always try to strictly tell the students whether to have 2, 3 structures. You discuss based on the functional group. For example, here, if I talk about 3 structures, using 3 structures, discuss naming of monosaccharide based on the functional group. So the way I've explained, you talk about the functional group. We have aldoses, where the aldehyde group is at carbon atom number 1. Give examples of those aldoses. 2 for sure. 2 and 1 are ketose, or 2 ketoses and 1 aldose, because there are 3. So you either choose to put 2 of the ketoses structures and 1 aldose, or 2 of the aldoses, 1 ketose, the way you choose. But if I would have talked about 3 structures, using 3 structures, discuss naming of monosaccharide based on the functional group. So mention the functional group, mention the carbon where the functional group is, draw the structure, highlight the functional group. You'll get all your marks. We talk about, there are some things which are direct, which I'm not going to take much time on. Now this one I have to describe, I have to discuss on the board, because we did it, some student hadn't reported yet. And I said, I can set this one, pH of water 7, and buffers. Any of those I'm allowed to set. So let's look at water. I said, using a KEQ value of 1.8 times 10 to minus 16, prove that the pH of water is what? Is 7. We said, when water dissociates, I have to divide my board. Then I'm going to push it so that you can see. When water dissociates, you are going to get hydrogen ion and hydroxyl ion. The dissociation constant is known as KEQ. And I said the KEQ is equated to KW, which is autoprotolysis constant of water. We already have KEQ as 1.8 times 10 to minus 16. It has to be minus 16. Then you talk about the KEQ, which is the dissociation constant of water, is equated to concentration of hydrogen ions, whatever is to the right, concentration of hydroxyl ions, over whatever is to the left, concentration of water. Meaning, if you're talking about the concentration of water, you are talking about moles per liter or molarity. So you say, if you look at water itself, based on the atomic numbers, oxygen is atomic number 16. We have only one oxygen there. What we want to look at is, we want to look at the value of water down here, concentration of water. And hydrogen, atomic number, atomic mass is always 1. And we have 2 of the hydrogens. So if you add 16 grams for oxygen plus 2 grams for hydrogen, you get 18 grams. But then the 18 grams, you say 1 mole is equivalent to 18 grams. What of 1,000 grams per liter? Then you equate 1,000 grams per liter times 1 mole over 18 grams. Cancel the grams. You can see moles per liter. That is the concentration. If you do your calculation, you'll get 5.56 moles per liter. That is the concentration. Substitute. KEQ was 1.8 times 10 to minus 16 equals to concentration of hydrogen ions, concentration of hydroxyl ions over 55.56. But you also, if you cross multiply, you'll have something like this, times 1.8 times 10 to minus 16 times 55.56. You equate to hydrogen ions concentration, hydroxyl ions concentration. But the 55.56 should be in the same way as 1.8 times 10 to minus 16. We should put it to the base 10. So you will have, you have to move 2 steps back times 10 to power 2, meaning a positive one, you will move 2 steps, then you will initially come to the value which you started off with. So this one you equate to hydrogen ion concentration, hydroxyl ion concentration. Then if you multiply 0.556 with 1.8, you'll get 1 times. Now we have the powers. Meaning when there is multiplication, you are going to plus. You add the powers. You will get 1 times 10 minus 14 equals to hydrogen ion concentration, hydroxyl ion concentration. Then what you do here is you say pH equals to negative log of hydrogen ion concentration. But now you can see we have hydrogen ion concentration, we have hydroxyl ion concentration. So it means they are going to be equally distributed in the ratio of 7:7. But now, the definition of pH is negative log of hydrogen ion concentration. And if you go with the hydrogen ion concentration, then pH will be equal to the negative sign which is outside. Already there is a minus sign which is retained here and the 7 for the hydrogen ion. So the pH negative will cancel themselves and you will have pH of +7. So you have to show all that so that you can be able to know how the pH comes to 7. So at that point, it has to be -16. If it is not -16, raise up your hand. The KQ value, that is always the value for KQ. So you can't create your own. On the same note, I'm going to derive the Henderson-Hasselbalch equation such that when we reach there, we shall pass because we are almost. But then I would like to combine the Henderson-Hasselbalch equation with the one for deriving the pH of water. Any can be brought. You will not choose that, Madam, bring for us this one. I can bring any, and even tomorrow I can bring any. It can be this one for water or the one for preparation of buffers in the lab. The Henderson-Hasselbalch equation. We say that's how important the buffers are. Maintaining the physiological pHs in our bodies. The buffers are always used. For you to conduct those practicals in the lab, the buffers are always used for those practicals which are done in the lab. So for the buffers, we said that you start with HA. HA goes for weak acid. Weak acid dissociates to hydrogen ion and A minus. And you talk about weak acid, the Ka. That is the dissociation constant of weak acid. It means, just label this one, weak acid, because a buffer is having a component of weak acid and conjugate base. This is the conjugate base. This is a proton, you know, conjugate base. Those are the components of buffers. Now, we want to derive the Henderson-Hasselbalch equation, just as we did for water, where we start with KQ, do Ka, whatever is to the right, concentration of hydrogen ion, concentration of A minus or conjugate base over concentration of weak acid. Here, we were going step by step. Roman 1, make hydrogen ion concentration the subject. That is what we wrote on the board. Make hydrogen ion concentration the subject. So let's write it the way it is. The way it is. The way it is. Start by multiplying. Whatever you do to the right, do to the left. Whatever you do to the right, do to the left. Then you'll have Ka, Ha equals to H plus A minus. Meaning the first step of making hydrogen ion concentration the subject, it finally comes here, where we have, yes, where we have, so this one you have to cancel themselves, where we have Ka, Ha over A minus. You've made hydrogen ion concentration the subject. Of course, everything, you'll do all the questions. No compulsory, no option. It's a cut. You are going to have 70 marks. You have to do all my equations, which are 70. There is no option. Everything compulsory. And I told you that the first cut will be a determinant. Second cut is only 10 marks. So we have to pay attention. So I'm saying we are making hydrogen ion the subject. You get. So the second point here is you are going to introduce log. Introduce logs. So write log hydrogen ion concentration log Ka. There is a multiplication in there. Put a plus log Ha over A minus. Number 3, introduce negative sign. Negative log hydrogen ion concentration equals to negative log Ka. A negative and a plus is what? Is a negative log Ha over A minus. I'm trying to put it there so that we focus this side. Yeah? Next, we said in class that pH equals to negative hydrogen ion concentration, negative, no, pKa, not negative pKa. pKa equals to negative log Ka. Substitute. Now pH equals to pKa, still minus log Ha over A minus. But in mathematics, the law of reciprocals, if it reciprocates, it's a minus. So just like if you do 1 over 2, it means 2 minus. 1 over 3, 3 minus. So if you reciprocate, it means there is a minus sign there. pH equals to pKa. The minus will cancel, it will be a plus. Log conjugate base over weak acid. That is the Henderson-Hasselbalch equation. Any can be asked. Derive the pH of water as 7. Derive the Henderson-Hasselbalch equation, or derive the equation which is used in preparation of buffers in the lab. Simple as that. Question number 15, Roman 2 says, show a reaction on how water acts as a buffer. A reaction where water acts as a buffer. You know, water can act as both an acid and a base. Don't stress yourself and write a lot of issues. No. This equation, you could remember when you were looking at the last characteristic of water. This equation, you could see it very well, where it was forming hydronium ion. That is the equation I want. You see, it donates. This one receives. If this one donates, you can see, this one donates. So it is going to, this one is going to form what? One will be the acid, the other one will be a base. So that is the equation I want. If you could remember where we drew that, where we wrote that equation, sorry, we didn't draw. You don't draw an equation, but you write an equation. So where we wrote that equation where water acts as a buffer, only 3 marks. Each one of those is going to score marks. You see those ones? Whatever I'm writing there, going to score marks. Discuss 2 water properties Crystal structure, biological solvent, that is very easy, because that is not which you can read, but what you saw with all these properties of water, the dipolarity was standing tall as to give much about the characteristics of water. So something which somebody can read and understand, I don't explain much, because it's like I'm repeating whatever we wrote in the notes. What I need to stress much are the structures, very important. Question number 6 says, question number 16, sorry. It says, classification of amino acids based on the number of carboxyl and amino groups. Based on carboxyl and the number of amino groups. And draw structures of any 10 monoamino, monocarboxylic, and you are the one who is going to tell me in the chat. The monoamino, monocarboxylic are which ones? If you look at the structures from whatever you read, we have the glycines, all the aliphatics, right? All the alcohol containing, right? All the sulfur containing. So I've just said 10 because I'm trying to make life simpler for a student there. Nobody can't know how to draw glycine, alanine, serine, cysteine. You shall have gotten even 10 marks, surely. So we are trying to accommodate all the students. If you revised well, getting a 10 in that question is not difficult. And then I talked about 2-diamino dicarboxylic. Last time you could remember, diamino dicarboxylic are the amides of acidic. The amides of acidic are asparagine and glutamine. Then if you have 10 of the aliphatics, 6 of the aliphatics, sorry, you have the serine, you have the methionine, you have the threonine, you have the cysteine. That's already 10. You can add phenylalanine, you can add tyrosine. So you have options. And then with their 1-letter code and 3-letter code, it's an easier as a pizza. Now, question number 17 says what? Discuss disaccharides. This is what I want to draw. You can discuss the disaccharides now here. Wanasema unajifungua, unafunguka roho. You can see it's 20 marks. You write about sucrose, whatever we wrote about, non-reducing, the type of glycosidic bond found, the specific monosaccharide components, you know, all the stories you know about glucose. Yeah? You write all the stories, but of these stories, don't write things which do not make sense. Write things which make sense. And I said, when you're talking about these disaccharides, kindly, don't just throw words in lactose that there is galactose and glucose. Say beta D galactose, beta D glucose. On sucrose, say beta D fructose, alpha D glucose. For maltose, say, for me, for my case, because I said the second carbon monosaccharide component is a beta D glucose. So say beta D glucose and beta D galactose, beta D glucose and alpha D glucose, sorry. So you have to mention the monosaccharide component, because if you throw galactose and glucose, the linear form does not form the disaccharides. It is a cyclic form. That is why I want you to stress on the alphas and betas. Because if you throw for me the glucose and glucose in maltose, I'm going to give you wrong. Or I'm not going to mark it. Sorry. So you have to specify whether it's a beta or an alpha. Now, I mentioned last time that when drawing fructose, I will check by the first monosaccharide component. It just has to be, it will have to be a must. It has to be a galactose. Look at this one, OH. This one tells me it is a galactose. It is a galactose. Then this one, it is above. So you will go up, come down, go up. Then we have our glucose here. Beta. Beta. That is lactose. Then you have maltose here. Alpha. Alpha. Sasa, the alpha, it easily go down. Look at that. You can easily extend the glycosidic bond downwards. That's how simple it is. But this one is a beta D-glucose. If you know the linear form, cyclic form is very easy. No stress. Cyclic form, very easy. No stress. That is maltose. The last one is sucrose. The last one is sucrose. Sucrose is here. You have you know, fructose is going to form a furanose, but remember, there is no OH here. That's why it is non-reducing sugar. That is carbon atom number 3, number 4, number 5, and number 6. So the drawings will get much marks. More marks will go for the drawings. But you have to describe everything that you know. All that you know about these disaccharides. Let me see the questions. Please draw sucrose. It is a bit confusing at a glycosidic bond. The sucrose is down there. Can you see it? Mukhtar, Sabir. Mukhtar. Can you see down there? You know, the reason why sucrose is confusing, I'm trying to bring it a bit up. The reason why sucrose is confusing, you know, the glycosidic bond, the 1,2. They talk about the 1,2 because the 2 is the keto group where the attachment goes. You talk about number 1, number 2, number 3, number 4, number 5, number 6. If you look at the other version, which could be, it could be, is it the one which is on the channel? You'll see there is a straight line coming from the D-glucose up there, down, connecting to the fructose. So the two which you see, the alpha 1, 2, the 2 is the keto group at carbon atom number 2 for that fructose. That is where the confusion comes. So don't get confused. It has to be 1, 2. And there is a version which draw it like this. And that is the version which make the 2 to make sense. Let me show you. Let me show you that version and you'll be able to understand. So it comes here. It comes here. That is the version which brings the 1,2 very well. You see, some books you are going to see something like this. You can see it's an alpha on glucose. I'm answering Mukhtar. Mukhtar, look at that version to my farthest where I'm trying to focus the camera. You can see 1, 2 at carbon atom number 1 on D-glucose, the OH is below. Some books are going to draw sucrose like that. It's still correct. And even the one which I've drawn is still correct. So it clearly brings the 1, 2. Sorry, where is the second carbon atom for fructose? Can't you see in my second drawing? The keto group there, Cornelius, the keto group there, the second version brings clearly the 1, 2. So now it does, where you can see the CH2OH is always the first carbon atom. And then there will be the second carbon here. This is carbon atom number 1. Let me highlight the numbers. Carbon atom number 1, number 2, number 3, number 4, number 5, and then number 6. So it has 1, 2 alpha carbon atom. That is how it works. That is what I'm telling you, Cornelius. The first structure shows that the second carbon, it shows the keto group on fructose. It will clearly not show like that. But in the second one, it will show. So in the first structure, it shows well that at keto group, the second carbon is where the keto group is, and that is where the bond is. So then it brings the alpha 1, 2. The 2 is the keto group, where it is. So either way, if you draw it the way it is here, the way I do it in class, or for some books on the channel where you can see this one, for my BMLS upgrading, their lectures have this one. And I think even for the channel, it is the second one. So what we have to know here is the keto group, the 1, 2. The 2 comes from the keto group. So don't get stressed, don't overthink so much. We are talking about question number 18. We are almost there, which now by students, you know how to draw the structures of the amino acids. So we need not to draw much. All aliphatic and sulfur containing. So I need the structures of glycine here, alanine, valine, leucine, isoleucine, proline, and methionine and cysteine. Why do you want me to draw peptide bond for Frank? And K is not, was there K? Was there K? Why should I draw for Frank? Do you genuinely want to know how to draw a peptide bond, or you are testing my faith? That is what I'm asking. Because I know the reason why. Me, I can draw Frank, but I know the reason why I can't do for you that Frank. Because the students will be complicated with drawing the arginine. The R is arginine, right? K was what? Did you see any K as one letter code? I didn't see any K. Agnes. Okay, for lysine, good. What do you want to know? Why do you want Frank? The reason why I will not do that Frank, because R for arginine, for most students, me I can draw. Or the R side chain for arginine. So it means, you know, when we were drawing the arginine, we had put the R side chain to the side, right? We had put the R side chain to the right, but if you put it to the right, then definitely you are right. You are right, Agnes, because it might confuse you and you don't know where to place what? The peptide bond. So when I'm done, I'll do the frank, which you need. But for now, let us look at the other question. Then I'll revisit that, because you've told me you genuinely want to know. It's at the carboxyl terminal end and amino terminal end. But what I'm telling you here is, arginine might be complicated to some of the students. You get? But I can also draw it. Before we can proceed. Let's see how frank will look like. So you have to do F, you have to do R. Arginine will get a very good big space. If you put the R side chain downwards, if you put the R side chain downwards, then definitely you will be able to know. Let me just see how I balance. If you draw the individual amino acids, it's always very easy to know how to balance. Those 1, 2. I think here there was a double bond, but it will be excess, no? It should not be there. NH, NH2, NH2. 1, 2, 3, 1, 1, 2, 3. Something is amiss. Let me see. Yes. Good. Now I got it right. One, 2. Yes. That is arginine. Phenylalanine. Alanine. Asparagine. Lysine. 4 of the CH2s. So let me see. If you look at that, Agnes, if you look at that, you see the structure of arginine. I told you, if you put this amino acid, the R side chain, to where the position you can see, to the north, to the south, down there, you can now see the clue on how to draw the peptide bond here. Water will be removed here. Water. I'm still looking at the space where I'm going to draw the peptide bond. It means I'm going to rub. I'm assuming you've drawn what? The individual amino acids. Agnes, you've got your 1 mark each. Now the peptide bond will come here. I'm rubbing because my space is too small. Carboxyl group, amino group. Arginine is here. Carboxyl group, amino group. Carboxyl group, amino group. Then carboxyl and amino. Then you write plus how many places? 1, 2, 3, 4. 4 water molecules. But you know, for arginine, it deserves even more than maybe 6 marks. Not 6, but 7 marks. Because even getting the arginine structure right. Agnes, look at that. I've assumed that the first structure, the way it looked like, you've already scored 1 mark each for drawing the correct individual amino acids. Remember, we drew it across because the board, we are trying to accommodate everything on the board. But the main issue here is attach the carboxyl to the amino, carboxyl to the amino. Where there is the peptide bond, a water molecule is released. Agnes, tell me if you are fine or something is still not clear. Then now I can proceed with the questions. I finish. The students can go and sleep. So for the ones which we can support by discussing in notes, the way we wrote the notes, then it's okay. But for the ones which genuinely need, thank you so much. The ones which genuinely need structures are the ones we are stressing much on, so that you can know what to answer, because I really focus much on structures. So we are almost there. For the ones who are already feeling tired, we already talked about all aliphatic and sulfur containing, where I said, give me all the aliphatic and the sulfur containing, the way we had. We have 2 sulfur containing and 6 aliphatic. Discuss criteria for naming of monosaccharides, still 20 marks. This one is repeating itself from whatever we had in the previous. So naming of monosaccharides, we already talked about the functional group and the number of carbon atoms in the main skeleton. And then the last question talks about the nutritional classification, still 20 marks. I told you, directly telling you to draw amino acids, it's rare for me. But in the essays, we can look at different classification of amino acid. We looked at the structural classification based on the R side chain. We looked at the charge. We looked at nutritional classification. We looked at the number of carboxyl and amino group. So they can easily be tested in essay. Any of those classifications, not all of them, no. Any of them, of which you have to define essential and non-essential amino acids. That under non-essential and essential amino acids, I want 5 structures of amino acids in each of those class. In essential, define the essential. If you have to remember those amino acids in essential, give me any 5 and their structures and their 1-letter codes. For the essential, I also need 5. Their 1-letter code and 3-letter code. That's it. So all the best for tomorrow's cut. For the people who started reading early, of course. But if you started to read today, I don't know what to say. But you'll be putting a lot of pressure on your brain and everything. And by tomorrow, you'll forget everything. So if you started early, because it's good to start early, so that now you just try to peruse as you try to remind yourself whatever you've been reading, if it's correct. So I say all the best. Tomorrow the cut will start at 10:30, and let us all avail ourselves there so that we can do the cut. So don't bring for me an excuse, Madam, I don't give makeup cuts the way you see me. That's why you can see my cut. I take time. Before I can announce my cut, I take time. So you have to avail yourself. Not a matter of always give it. I don't always give a makeup cut. So welcome. For somebody who has said thank you. I hope it was of help to the students. So you'll be able to adjust that which you didn't understand, and that's okay. So we are going to set, I'm going to set where we had reached, from where we started until where we reached the other time. And then we'll be able to finish with the remaining part of lectures. Then at cut 2, which is in 2 weeks' time, we'll be able to do the fatty acids. Correct. Essential and non-essential. Correct. That's what I meant. So you people have a nice, not a nice evening, but have a good night, and see you tomorrow, God willing. Thank you so much.